I'm going to show you a couple of different forms of the equations that Bohr came up that are useful for us. One of them is to say the electron is going to go from the initial state, so Ni equals the initial quantum level of the electron, and then Nf is the final quantum level of the electron. Okay, sometimes I'll put in parentheses, it's written as N1, as it was in the Rydberg equation, and N2. But that can be a little bit confusing because the levels could be 1 and 2, so N1 might be 2, and that could be confusing. So it's not a bad idea to use N initial and N final. So one of the equations is that the difference in energy, so this is how much the energy of the atom changes. So I'm going to write atom just so that we have that written here. That would be equal to minus 2.18 times 10 to the minus 18 joules times 1 over n final squared minus 1 over n initial squared. So that's one form of the equation, or that's one equation you can use. Okay? Now, the energy of a photon is equal to h times the frequency, h nu, right? Remember, this is Planck's constant. And that has the value 6.626 times 10 to the minus 34 joule seconds. And then the frequency, oops, let's spell that correctly. Frequency, and that's typically in hertz, or 1 over seconds. Okay? So the energy of the photon, what happens is the energy of the photon, or the difference in energy of the atom, is going to be equal to the energy of the photon, right? That was one of the things that Bohr said. So we can connect those two. Now, when we make measurements of the atom, we generally measure the wavelength of the light coming off for various reasons. The wavelength of light that's being emitted by the atom. So let's make a little room here. Okay. So I'm going to show you another form. This is from your textbook. 1 divided by the wavelength of the light that's emitted is equal to 2.18 times 10 to the minus 18 joules over Hc times 1 over n final squared minus 1 over n initial squared. Again, let's erase this. There we go. Okay, so here's another form. This is another form of the equation that can be pretty useful. If you're doing a problem where they want you to determine the wavelength of light that's emitted, a particular line from the spectrum of hydrogen, this is not a bad equation to use because it's got wavelength in it already. So that could be pretty useful. It's interesting, if you look online, you'll find there's actually a bunch of different equations that are manipulations of this. I'm not going to show you ones that are not in your textbook, but there definitely are other ones. So this equation can be used for wavelength. And I want to talk a little bit about units. So you'll notice that in the numerator you have joules, and then in the denominator you have Hc. So I'm going to do a unit analysis for this particular equation. So in the numerator we have joules. The units of H are joule times seconds. And the units of the speed of light, remember that's the speed of light? 2.9979 times 10 to the 8th meters per second. Well, the speed of light is typically in the units of meters per second. So that means seconds divided by seconds cancels, joules cancels, and you get 1 over meters. So what would we expect the units to be the n values are unitless. They don't have any units. They're just counting numbers. So we would expect 1 over wavelength to be 1 over distance units, and that's exactly what we get, 1 over distance units right there. Okay, so be aware that it's not uncommon to have to do nanometer to meter conversions or vice versa, but this equation, the way it's written, is going to give you units of 1 over meters. It's not going to give you nanometers or 1 over nanometers, so be aware of that. Now, the last point I want to make in this section is the difference between absorption and emission. Okay, absorption versus emission. Essentially what happens is, for the hydrogen atom, the relative energies of these levels, right, n equals 1, n equals 2, n equals 3, n equals 4, they look something like this. So this is on the y-axis, this is energy. Okay, so energy on the y-axis. So n equals 1 is the case where the electron is closest to the nucleus. N equals 2 is further out. N equals 3 is further out. 4, 5. Notice how they're getting closer and closer to each other. This is called a convergent series. They're converging on another. In fact, infinity might be somewhere up here, or n is approaching infinity. Ionization, the electron's no longer on the atom. So the difference between n equals 6 and n equals infinity is significantly smaller than the difference between n equals 1 and n equals 2. Absorption is the case where the electron is promoted to a higher level. I'm just going to show one of those transitions here. This would be n equals 1 to n equals 3. So if the quantum level is increasing, that's called absorption. The energy is absorbed by the atom, so we call it absorption. Now, what happens, what's the opposite of that? So I'm not going to show you a different one. I'll show you the same one. N equals 3, n equals 4, n equals 5, n equals 6, and then n approaches infinity. Right? 1, 2, 3, 4, 5, 6. Suppose the electron goes from 3 to 1. Now it could go 3 to 2, or it could go 3 to 1. Okay? So n equals 3 goes to n equals 1. Each of these are called transitions. Each of these two processes. Right? The electron is undergoing a transition from one level to another. The difference here is that when the electron jumps down to a lower level, if the final value of n is smaller than the initial, in this case, a photon can be emitted. So your photon comes out. So this is called emission. Okay? So absorption, the electron goes to a higher level. Emission, the electron goes to a lower level. So in a light bulb or in one of these gas discharge tubes that we talked about in the first part of video of this section, what's actually happening is the atoms are moving so quickly, their energies are so high due to the high voltage that's applied to the discharge tube. Let me show you, come back over here to the first picture. What happens is those atoms right here, they're moving so fast, each one of them is absorbing some of the energy due to the kinetic energy and due to the high voltage, that the electron jumps up to a high level and then pops back down on its own spontaneously. And then it might go back up again and then come back down and go back up and come back down. So back and forth, back and forth. Every time it comes back down, it will emit a photon. So it absorbs the energy from the power source, but then emits that energy in the form of a photon. It's not 100% efficient. Sometimes the electrons will jump down to a lower level without emitting a photon. They have other mechanisms of It's very difficult for hydrogen atoms to do this, but they can, in theory, release energy in different ways. Okay, and there you go. So that's section 6.3, Bohr's theory of the hydrogen atom. Of course, the practice and sample problems are very important for this.